Welcome to a new video about inverse Z transform. This is our example number 2 where we consider another example. Of course, we will work out everything step by step in our calculations and also verify these in MATLAB using the command window. Now we have here a function. We would like to determine the inverse Z transform of this function, and this function is similar to the example number 1 where we had also a 0 at the origin here. In this case we don't have that 0, so we will see how we then solve this problem. Okay, let's see first the calculation step by step. We start first dividing our function given here by z. That's now shown here, so you divide this by z, you get now a z in the denominator. And now we need to use the partial fraction expansion. So we set this in the partial fraction expansion. What we will see here now that we have a z fraction here, another fraction, so we have now 3 parts, so we'll also have 3 fractions. That means we have now 0.4 over the z times z minus 0.5 times z minus 0.6 will be now divided in 3 fractions as shown here. So we will now determine a, b and the c, those coefficients. So we will now also take these 3 coefficients, the 3 fractions in one fraction by making these denominators the same. So we need to have that also the same. In order to do that, we can multiply the a by the z minus 0.5 times z minus 0.6. That's shown here, so they have now the same denominator. That's also similar to that b and also for c. You can actually see the procedure. Now we can add them up because they have the same denominator. So we can go here. Now we have this numerator here divided by this denominator, which has also the same here because this left side has the same denominator. Now we can say the 0.4, so the numerator of the left side must be also the numerator of the right hand side. And that's shown here. So we can use this equation to determine a, b and the c. Now we can again use the same procedure as we did in the previous example. We select a value for z such that one unknown is left, so we can select now the z is equal to 0. Why? Because then the b and the c will disappear because that will be then multiplied by 0. So you can see that effect here, so it will be then 0.4 the left side and then a times this. Just substitute here the z is equal to 0. This will be 0, this will be 0 is actually shown here in detail. So we get now here 0.4 is equal to minus 0.5 times minus 0.6, which is then here 0.3. So you get actually here now 0.4 over 0.3, which is then equal to 4 over 3, exact. Okay, next one is again a selection of the value for z, but now we would like to eliminate b or c in order to calculate also those two. Now we can set z is equal to 0.5. Why? Then we eliminate a here, as we have here. I need to point it out here. And also we also eliminate the c. So we have actually this one in detail. Then we have left only b. So that means 0.4 is equal to, here you see here, minus 0.1 times 0.5 will be then minus 0.05 times b will be then 0.4. So the b will be then equal to this, in this case exactly minus 8. Now we need to select another z in order to also calculate the c, and that is looking at the expression here again, and we can select the 0.6 because then we lose the a and the b, but c will be present. So we have here the expression. You see again, everywhere where we see a z, we substitute the 0.6. We lose the a, we lose the b, we only have the c, and that is effectively 0.4 is equal to 0.6 times 0.1, that means 0.06. And we have here 0.4 over 0.06 for the c. That will result in 20 over 3 in the exact form. Okay, then we can write this expression which you have here, because the a and the b and the c are now known. We can write it like so. The fz, which is our function over z, is then 4 over 3 divided by z, minus 8 over z minus 0.5, and 20 over 3 divided by z minus 0.6. Okay, now we need to go to the next steps in order to calculate the inverse z transform, because this was the step we wanted. We can now multiply the left and the right hand side by z in order to have the function again. That is the fz, so you multiply this by z, so you lose the z in the denominator. You have here z in the numerator, and you also have the z here in the numerator, so you can see that clearly here. So let's use this table from the z transform to the sampled time function, so the inverse z transform, and see what we need to do. So if we have a constant, we need to multiply that by delta or canonical delta function as shown here. And if we have a expression which says z over z minus a, which is a is a constant, m is a constant, then we need to write it like so. And we actually have that. So we have here a constant. We also have here z over z minus 0.5. So that is then our a, and another one here 0.6. So in the similar case, we need to use this once and the second row twice. Time function at the sampling instance can be then written like so. You see here 4 over 3 with this direct delta function from the first entry, and the minus 8 because that's just the m here, and then times 0.5 to the power k, which is in this case a, and for the second one, the final form is 20 over 3, which is our m, and then times 0.6 to the power k. And this is valid for k is equal to 0, 1, 2, 3, and for lower value of 0 it is 0. Okay, now let's take this function here and also go to the ideal sample time function, and that's given by this f star in time domain. We take this function, which is of course only valid between for 0, 1, 2, 3, etc. in integer form, and we just also look at that in this delta expression. So if we substitute, for example, k is equal to 0, 1, 2, then we have the first 3 samples of the ideal sampled waveform. So how does it look like? So if I look at this expression, I can say it's 4 over 3 times the delta of 0, and then minus 8 times 0.5 to the power 0, which is actually shown here, and then 20 over 3 times 0.6 to the power 0, and then the direct function or delta function, and then t minus the 0t, which is actually shown here. In a similar case, you now change the k's to 1, 1, 1, 1, and then next time 2, 2, and you actually go on to infinity. So in this case, we have now our first 3 samples. Now we can, of course, simplify this because this one is 1, 4 over 3 times 1. This is then minus 8 times 1, and this is 20 over 3 times 1. So in total, this one here in the parentheses will be 0 times this, the direct function t minus 0. So this is actually this part. And this happens to be also 0, this second part. So you can actually calculate it for yourself also. And that will be then this part. So 0 times t minus the capital letter T. The third one, which is this one, will be equal to 0.4. So t and then delta function t minus the 2t, 2 capital letter T. And if I go on to the case 3, you get this, and case 4, you get actually this. So you can move on and then see all the sampled values. Now in MATLAB, you can check that. So let's see also that this is indeed correct. Now we start first with defining our symbolic scalar value, in this case z, which is our variable in our function. This is the function we have given, which is 0.4 over this z minus 0.5 times 0.6, and that this is the expression for our function. And this command here, iz trans in parentheses capital letter f, is equal to the small letter f, will determine the inverse z transform, and which is then actually shown here. So this is the result. Now you can also make this a little bit easier to read because these are all fractions, everything is in exact form written. You can also say I would like to have it easy to read, so you can also look at this result in some digits, and that is also shown here. And let's first compare the expression we have here, the result, with the expression we have here. Now what do you see here? You see here 4 over 3 times this direct function, which is actually shown here. So 4 times the canonical delta over 3, and this n means that is kt. And we have also this minus 8 times 0.5 to the power k, which is this second term, So the order is different, but it doesn't matter. And we have also this 20 over 3 times 0.6 to the power k, which is actually shown here. So everything is in place there. So, and again, this is correct. So again, if I want to also have it in a different form, convert the fractional values to decimals. In this case, I have chosen for 5 places. And you see here, this 20 times 3 over 5 will be then 6.6667. And this is then 0.6 to the power n. And this 8 will be then times 0.5 to the power n. So it's a little bit easier to read. And we have here 4 over 3 will be then approximately 1.333. So right, this was our second example, constituting inverse z-transfer of a function. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.